Okay, the first function we're going to write here is our calculate rotation matrix. Let's take that up here. We'll use our definition keyword. Now, it takes in position I and position j. Now, this function that I'm about to write, we wrote in a previous course in our 3D structures course. If I jump over to the Degree Tutor's website and show you the course, I just want to point out where we discussed the theory behind this function that we're about to write. All right, so over on the Degree Tutor's website here, if we go to courses, and go to the finite element analysis of 3D structures, this course here. In this course, let me see if I go all the way down to this here, building the transformation matrix. So in this, I basically go through, in this section, I go through in great detail the function that I'm about to write. So I will explain it to a certain extent, but if you want more detail on the how and the why of the various different bits and pieces, that's where you go to find it. All right, so what do I need to do? I need to, first of all, I'm going to define an identity matrix, a 4x4 identity matrix, which is going to serve as a template, and I'll override the various elements within that matrix. So using NumPy, I'll just call identity and pass in 4 that generates a 4x4 identity matrix. Next thing I want to do is unpack pos I and pos j and just identify or extract the individual coordinates, the x, y, and z coordinates of node I and node j. So that's trivial enough. I'll just paste that in. So just indexing off the individual values. Next, I want to define the difference in x, y, and z coordinates between the two nodes, basically the difference in x, y, and z coordinates. And from that, I can very easily determine the length of the member. So one of the pieces of information that we want to pass out of the bottom of this function is already calculated, the length. So let's just put in a note here. So function to return the element rotation component of the transformation matrix. All right then. So now that we've got that, we can start building up this rotation matrix. So what is the rotation matrix? It is just it's a 3x3 matrix, the pure rotation matrix. The first column is the element's local x vector represented within the global reference frame. The second column is the element's global y vector, and the third column is the local element z vector in a global reference frame. And so if your element is aligned with your global reference frame, that 3x3 rotation matrix would simply be a 3x3 identity matrix. And then obviously as our element starts to rotate within our global reference frame, its local reference frame that is locked to the orientation of the element will obviously rotate within the global reference frame, and then the components of those local x, y, and z vectors will change, and it will no longer be an identity matrix. And it's a really ingenious little way of capturing the orientation of an element within a 3D space. All right then, so what do I need to do? I need to generate the local z vector in the global reference frame. Now in this case, our z vector is going to be running along the element, right? So let me just take this cylinder here, right? Let me see, get this guy, and let's scale Shift Z just to make it a bit more, make sense to us a bit more. Right, so if let me just scale that in the Z direction. Let's imagine that's an element, right? One of our elements. You'll notice that what I've got here is the X, Y, and Z axis within the global, well, they're the global X, Y, and Z axis because it says global here. If I change that to local, you can see that this doesn't change, right? Because this thing is aligned, it's in its default orientation, and in its default orientation, it is aligned with the global reference frame. So what I'm saying here is the local Z axis of this element runs vertically along the element. And so to generate the local Z vector, I basically just have to take the coordinates of one end and take away the coordinates of the other end, and that's going to give me the local Z vector. So let's do that then. So we're saying the local Z vector in a global reference frame running along the member is going to be the coordinates of the position I minus the coordinates, or rather the coordinates of the position j minus the coordinates of the position I. We want that in a unit vector, so we just got to divide that by the length of the element. So we'll say the local Z unit vector is going to be the local Z vector divided by the length. Okay, that's fine. That's the first component of our rotation matrix. Next, we want the local X vector. Now, in order to get a local X vector, I need a vector that is orthogonal or at right angles to the X vector. Okay, how do I do that? I have to first of all define the local XZ plane. Okay, now to define a plane, I just need two vectors. They don't have to be perpendicular. They just have to be not collinear. They have to be two separate vectors. And those two vectors can define a plane. Now, once you've defined the XZ plane, well, then you can go ahead and use a process called the Gram-Schmidt process, a vector process, which allows you to take one of those vectors and calculate the orthogonal vector, right, the other orthogonal vector within that plane. So the key here is, first of all, we've got the local Z unit vector. That's fine. That defines the local axis running along the member. I now need a plane, right, that's going to define that ZX plane, right? Now, in order to get that plane, I'm going to take the coordinates at each end of my element and I'm going to offset them. And by offsetting them, you can imagine I'm generating a plane. Essentially, those four coordinates create a plane. I can then create a vector that lies in that plane that is not the Z vector, and I therefore have two vectors defining a plane. Okay, right. Now I've got two vectors that define a plane. I can use the Gram-Schmidt process to turn those two non-orthogonal vectors into two orthogonal vectors, i.e. vectors at right angles. And in that way, I have now got two of my three axes. I've got my Z-axis, which I already have, and I have, using the Gram-Schmidt process, I have my x-axis, which is perpendicular to it. Now, that's the hardest bit done. Once you've got the two perpendicular axes, Z and X, well, then you can just take the cross product of those two vectors and get a third orthogonal vector, okay, which is going to be our y-axis. And so that way you'll have an orthogonal vector basis. You'll have three vectors that are orthogonal to each other and serve as that local reference frame for our element. Again, I'm hitting you, if this is new to you, I'm sort of hitting you pretty hard and fast with how this all comes together, because most of the people that will be watching this will have already, seen the other course, and so I don't want to labor it too much. Okay, right, where to next? So we've got the Z unit vector. Now I need to get the local X vector. So I need to do an offset here. Now, if the member is not vertical, if it's any orientation other than vertical, all I have to do is take my two coordinates at each end and just offset them in the Z direction by some distance, and that's going to define the local ZX plane. However, if the member happens to be perfectly vertical, and I'll know that by checking whether the difference in the X and Y coordinates between the two ends, if that's 0, well, then it's a vertical member. Now, if it happens to be a vertical member, well, then offsetting in the Z direction vertically won't generate a plane for me, right? I'll have to offset in a different direction, and so I'll just offset in the X direction. So I need to check that first of all. So I'll say if the absolute distance between the X distance between the ends of the element and the absolute distance in the Y direction between the ends of the element, if that's a small number, if both of those are a small number, just put in any small number here, well, then I need to generate my offset coordinates, let's drop that in there, by offsetting in the global X direction, right, to define the ZX plane. So all I'm saying is I'm generating a new Y coordinate by offsetting by +1 in the X direction, node I, and a J offset set of coordinates by offsetting by +1 in the X direction for the J set of coordinates. Okay, so that generates now two new points. That's if the thing is vertical. Now, in most cases, it probably won't be vertical, and so the other option is to just offset in the Z direction. All right, so there we are, right? So same idea, we're just offsetting this time by +1 in the Z direction, and that's going to generate for me an I offset and a J offset. Now, why do I need I offset and J offset? Let's just imagine, sort of try and illustrate what I'm trying to say here. Let's take this, let's Shift D and duplicate it in the X direction. I want to separate that out. So let me tab into edit mode. Let me see, hit P and separate by selection. That generates a new element. So you can see up here in the outliner, I've got cube 01. Over here in the 3D view, tab out of edit mode, select this guy and tab into edit mode, and now what I'm going to do is hit slash on my number pad, and that goes into local view. So what have I done here, right? Let's try and illustrate that. Let's say imagine that was position I and I've got those coordinates, and that was position J and I've got those coordinates. Well, what I've done for this element, what I would do is I would take both of these and I would extrude. Remember, I'm essentially offsetting in the Z direction to get two new points. So if I extrude in the Z direction by 1, let's say, now what do I have? I've got a plane, right? Got a plane. So now what I want to do is I want to take this, let me see, I want to take this edge here and I want to identify the point along the middle, right? So I'm going to identify that point to visually demonstrate that. Let me hit subdivide. So that's going to be a point halfway along. So if I have that point, right, well, I could get a vector that goes between this point and this point up here, and that would be a vector within the ZX plane. So if I now join that, right? So now what have I got? I've got a vector that runs along the element, right? That's the Z vector. I'd also have a vector within the plane, right? Let's just call that, let's imagine that's node K, right? Just call that point K. So if I took the location, the coordinates of that point, and subtracted from it the coordinates of that point, I would have a new vector that lies in the ZX plane. And once I've got these two vectors, i.e. this line here representing a vector and this line here representing a vector, so that vector and that vector, I can use those two vectors using the Gram-Schmidt process to turn those two non-orthogonal vectors into a set of orthogonal vectors. And I'm going to get a vector that comes out like this, which is going to be in the plane, but perpendicular to the Z vector. I hope that makes sense. That's basically what we're going to do. So now that I have my I offset and J offset coordinates, what can I do? I can define node K as being the node halfway in between, which was that node there, right, that I've just selected. So node K is going to be the position of I offset, which is that position there, plus half of the distance between that guy and that guy, which is going to give me that point there. So that's going to be node K. Now that I have node K, I can use that to build that local orthogonal X vector. So I'll say a vector in the plane is going to be node K minus pos I, which is just going to give me that vector there. The local X vector, and this is the I'm not going to explain the Gram-Schmidt process. You can look it up, but it's a pretty straightforward operation that you can do. So what is it? If I go back here, so the local X vector, so this is a vector that is perpendicular to the Z vector. It's the vector in the plane minus the dot product of the vector in the plane and the local Z vector, and then times all of that by the local Z vector. And that gives you a vector that is perpendicular to the local Z vector. Great. Now I just got to turn that into a unit vector. To do that, I want the magnitude or the length of the vector I just created. So we're going to call that mag x, right? So that's just going to be the square root of each of the components of this vector squared. That's pretty standard stuff. And then I can get the unit vector in the x direction by taking that guy and dividing it by the mag x, right? And so that is your unit vector in the local x direction for the element. So that was your Z vector and that was your X vector. Right, great. The last one is the easy one. Okay, so the last one was to use the cross product of these two orthogonal vectors to get a third orthogonal vector, which is going to be the local Y. Local Y unit is the cross product of the Z vector and the X vector. Okay, so we've got a local Y unit, a local X unit, and a local Z unit, and they are all derived or based on position I and position J. So we can run this and calculate the rotation matrix or the orientation of any element within this 3D space. So now the next thing I want to do is just actually build the rotation matrix itself. So I'm going to, that's just combining the three vectors I had. So I'm defining a rotation matrix here as an array, NumPy array, and I'm passing in the local X unit, local Y unit, and local Z unit, and taking the transpose of that then is my rotation matrix. Now let's override within a larger 4x4 transformation matrix. The rotation component is the first three rows and columns, and so we can override those values within this 4x4 identity matrix, this placeholder. So we're overriding the first three rows and columns with the rotation matrix we just calculated, and then we can return it. Now I'm not just returning OR, I'm returning OR cast as a matrix from math-utils. That was matrix that we brought in up here, and we're also returning the length. All right, so that was quite a beefy function to complete, and that is the hardest thing, right? That's the bulk of the work here is involved in this function. Once you've understood this, the rest of this is a piece of cake. So now that we've got that, let's go ahead and do the next function, which was calculate transformation matrix. This is only a few lines. This is an easy one. In fact, let me bring it all in one hit and just explain it bit by bit. All right, what have we got? We're building the translation component. So all I want here, let me tab out of edit mode here, and I don't need that anymore. I'll delete that and hit slash on the number pad to go back into sort of global view. Change that back to global. What I now want is I need to take a default cylinder and move it into the position of each of my elements, which you'll notice the center point of the default cylinder is going to be bang in the center of that cylinder. And so I need to move that cylinder, that center point, to the center point of whatever the relevant element is. And so the translation is going to be, the translation that needs to be applied to the default cylinder is to get that center point to the center point of whatever element I'm looking at, right? And so that's the translation that I'm about to calculate. All right, so here it is here, right? So we're passing in the position I and j. Now, what's the offset? The offset is going to be the position of node I plus half of the distance between j and I, right? That's the translation to this that's required to the center of the element, and I'm just taking the transpose of it. Now I'm going to, using matrix here from mathutils, there's a helpful little built-in function here, right? If I pass this function, right, so from matrix I'm calling this function called translation, right? If I pass into that function the offset, which is just the x, y, and z offset, right, what that's going to do is it's going to manually, well, it's going to automatically, I should say, build a 4x4 transformation matrix. And all that's going to be is a 4x4 matrix. Imagine a 4x4 matrix, which is an identity matrix, but the last column, right, the first 3 rows of the last column are going to be the translation in the x, y, and z direction, right? That's all that's doing. That little line there is just building that automatically for me, so I don't have to manually build it. And then we're just returning the trans matrix here that we just calculated, the translation matrix. What's the next one? The next one is to actually generate the element. So we've done that function, we've done that function. We can calculate the actual world matrix for our element then. And then the next function we have to write is generate element. And this is just going to be some Blender boilerplate, right? Dropping it in here, generate element. It takes in the scale, takes in the length of the element, the number, and the force magnitude. And now we're just going to use Blender's basically boilerplate code to generate an element. So and you can Google this from the Blender API documentation. So add a mesh primitive, right? What am I doing? bpy.ops.mesh.primitive cylinder.add or underscore add, and then you just pass in a whole load of different variables, right? So I want the default, I think, is 16 or 32 or something, right? I only want my cylinder to actually have 4 vertices, right? So if I was to add a new cylinder here, right, add mesh cylinder, come down here, and if the default's 32, if I change that to 4, you essentially get a cuboid, I guess you'd call it. So that's the type I want to add, because I want to keep my vertex count quite low, as low as possible. The radius is going to be whatever scale factor I pass in. The depth of it is going to be the length. That's why I'm passing in the length. I could control the length by scaling within the world matrix or the transformation matrix, but I think it's handier to literally just generate a cylinder that is the correct length of the member in question. We don't want to be in edit mode, so we set that to false. Align with the world. Set the location. Default location is going to be 0, 0, 0, and the default scale is 1, 1, and 1. So that's going to generate us a cylinder. The next thing I need to do is, well, I don't need to do it, but I'm going to set the shading to smooth just because it looks nicer. So we'll say bpy.ops.object.shade smooth. Again, kind of like, how do you know how to do all these things, or how do you know what commands? You have to basically go through the Blender API documentation. I really still struggle with the Blender API, not a reflection of the API necessarily, but it's just such a deep and big API. I find it quite hard to navigate. So just a lot of persistence and Googling gets you all these various different commands. All right, so what's next? We want to get a handle to the cylinder that we just created. That's going to be this guy here. So cylinder is equal to bpy.context.object. Right, we're just grabbing the current object and assigning it equal to cylinder. Just gets us a handle to it. So I can grab cylinder, and I can call name, and I'm setting that equal to, and I'm just building up a string here, right? So it's going to be element, concatenating onto that as a string, the number of the element, underscore as a string, the force magnitude, and then just putting in kilonewtons. So I want my elements to be named with the axial force, or the magnitude of the axial force. And then the last thing I want to do is just return that element. Right, so that was a real marathon. There was a lot in there. Are we in a position, or I should return cylinder? Are we in a position to run this and see anything interesting happen? Let's have a look. In our main function, we're bringing our data in, we're setting up a collection, we're going to reach for elements, we're generating the element here and changing its position here. Let's try and run that and see. Before we do, let's take that and delete them. All right, now this might or might not work. Let's see what we get. Okay, so down here we see that we have an issue, right? So in the bottom left hand corner we're getting a script failed, so we failed somewhere. So if I bring in my console, all right, so I just sort of dragged my console in here just to see what the issue was, and it looks like I've got a typo. I've misspelled cylinder. Where have I done that? Line 84. Yep, there you go. All right, so let's hope that's all it was. So let's say cylinder. All right, let's delete. It's interesting here. You can see that was the very first element that we created. So you can see the string here. It's element. The element number was 0, underscore, and then the axial load, which was minus 7 kilonewtons. So 7 kilonewtons in compression. Right, let's just delete that and delete the hierarchy that got created. And let's try that again. All right, bang, there you go, excellent. So you can see what's happening here, right? So we generated an element, we changed the orientation, or we calculated what the orientation should be, and we moved the default element that got created to match the orientation and location of the current element. All right, so you can see if I look in the outliner, you can see these are all the elements that got created. We haven't written the code to merge them all yet. And so this is fine if you've got a small structure like this. In fact, it's actually even easier if you have a small structure not to bother merging them together, because you can just select one and then straight away see in the outliner which element you've selected and what the axial force is. That's actually really handy. But if you get to a bigger structure, you know, Blender will start to slow down if you've got thousands of elements in here. All right, I think we've probably got enough done for this video. Let's take a break and come back in the next one, and we'll start thinking about coloring these based on the axial forces.